Thank you, Brett, for that very kind introduction. It's a great honor and privilege to be here. It's wonderful to be back in Florida again and see friends. Can you hear me? Is it okay? Back in the back? Okay. Well, you mentioned Norm Breslow and the Pony Express, and so I can't help but tell a story before I launch into this. When I was a graduate student at the University of Washington, Norm and his current PhD student at the time, John Crowley, were off in France, somewhere in France, Geneva, I think, and they were studying the Kaplan-Meier estimator. And they were in the midst of doing the first proof of weak convergence of the Kaplan-Meier estimator. Well, in those days, it was almost Pony Express. It was pretty bad. So I would get a handwritten letter from John Crowley coming from Geneva. He'd say, "John, would you please go to the math library and look up the such and such issue of the Illinois Journal of Math and look for this paper by Dick Dudley." And I would go to the math library, conscientiously copy it off, send it by regular mail to Geneva. Can you imagine that corresponding thing nowadays? Things have just changed so dramatically in between. And that process was part of what got me interested in weak convergence theory and the Kaplan-Meier estimator, and it led to this paper with Jack Hall and other collaborations with biostatisticians over the years. So this history I'm going to give today is going to be a very eclectic, bizarre history in some ways. I've never given a history talk, and I thought maybe I should try once in my career to give a talk about the history. And so it's going to be very funny and eclectic, and you probably won't learn too much real history. You'll get my biases about some of the beginnings, and it'll compress toward the end, and I really won't do too much about recent history. I'll compress the recent history into one slide or something. So I'm going to start with just some very early history definitions. And what I call the first period, which went from 1928 to 56, involves Kremer up to Kiefer and Wolfowitz in about 56. And then a transition period that overlaps with that, starting in about 53, but maybe really a little bit earlier, depending upon how you count. And you see some names there that I'll mention. That period really, for me, ends in the early 70s with the papers by de Hart and Vapnik and Chervonenkis, which give us really solid Glevinko-Cantelli theorems in general. Part of the reason for doing this history is over the years I've been asked these awkward questions about naming of things. So I have a student in a short course recently who asked me, why do we call it the Glevinko-Cantelli theorem? Why shouldn't it be Cantelli-Glevinko? And I didn't have a good answer at the time, and so I had to do a little bit of sleuthing. This one turns out to be pretty easy, and I'll give that one as we go along. But then the final period, starting about 67, again overlapping with this transition period, begins with papers by Dick Dudley and going up through Ledoux and Talleyrand and Ginet and Zinn in the early 90s, and some really phenomenal work on the bootstrap for general empiricals that happened in that period. And so this talk is about the interactions of probability and statistics. Probability theory on the one hand, guiding the mathematical side, and statistical problems providing impetus for the statistical questions. And the empirical distribution for me and its convergence to the truth is just one of the fundamental things that our livelihood depends upon. I tell my graduate students when I teach the theory course in statistics that if the Glevinko-Cantelli theorem were not true, I'd be out of a job. I would be out of work. I might as well be a ski bum. Well, I came close to that at times, but it could have changed professions. So I'm very glad Gulbenkian-Cantelli is true. It's kept me out of the bars and working on statistics for a long time. So here's the start, the very early beginnings. The first paper in which this funny function appears, well, we start with x's. Observations, IID from some distribution f on the real line. And so I'm dealing with real valued quantities at this point. The empirical is just the function, the random function, which records how many of those xi's fall to the left of a number little x. So it's just this proportion, that count divided by the sample size. Well, that's the empirical distribution. That's the thing that we use to estimate that true f. This first appeared in Kremer in 1928, then in Kolmogorov in 1933, and this series of 3 papers were all in the same journal. And it's kind of interesting that this theory all started with actuarial journals. So the Kremer paper was in the Scandinavian Actuarial Journal, so many pages. Kolmogorov in 1933 is in the Italian Actuarial Journal, and it went from pages 83 to 91. Gulbenko's paper followed immediately thereafter, pages 92 to 99. Fairly short papers. These aren't 30-page papers. But Cantelli came last, and he was on pages 421 to 424. And that's very interesting. That's why we have Gulbenko-Cantelli, in a sense, because Cantelli's paper came second. But the story is a little bit more complicated. Cantelli was by this point a fairly senior guy in the Italian actuarial statistical world. And he had founded this journal in 1933, and he was the editor of this journal from 1930 until about 1958. So quite a long period. And he was editing the journal, so he had a lot to say about these papers getting in, and undoubtedly a little bit to say about his own paper getting in. And so that whole history is why it's Gulbenko-Cantelli, I think. Now what they did, what did they do? Well, here's Kremer, long-lived. Kolmogorov, again, fairly long-lived. Cantelli, Paolo Cantelli, also pretty long-lived. Actuarial stuff coming to the fore, or good genetics, one of the two. Well, the other name here is Richard von Mises, and his paper was in it's not a paper, but it's a book that he published in German in 1931. And he was a little bit harder to get hold of in terms of looking at the original. I actually did get a hold of his book. But is this really the earliest? Well, in a sense, not, because Francis Galton, back in the 1870s, proposed plotting the ith largest of these xi's, the data, at I. So you order the data, plot it at I, and this is essentially the inverse empirical distribution function. Now, this is according to Ron Pike, and I really haven't chased this down in detail yet, but if this is correct, the empirical is essentially here, and we had the quantile function, the inverse empirical, going long before we had the empirical. Now, he didn't do much with that, not much theory, but these other gentlemen who've been on the slides so far, did do considerably more. So what did they do? Well, again, I'm repeating myself. We have a sample of X's IIDF. The empirical distribution is Fn. The question, is Fn close to F? In what sense? Or can we test that the distribution generating the data is a specified thing F0, or is it not F0 for a continuous guy? And Glavinko and Cantelli were treating the first question, is it close? And do we have convergence of some metric distance? And in their case, they were studying the Kolmogorov or supremum distance of the empirical to the truth. Kremer and Kolmogorov were more concerned with sort of a testing framework. And Kremer in particular was interested in testing F0 being the standard normal distribution function. And amazingly, in Kremer's paper, he actually dealt with data. And he had about 5 or 6 data sets. And he was trying to determine if the Gaussian law, the standard Gaussian law, was a good approximation to those data sets. Well, here's, first of all, before I show you that data, here is what Glavinko and Cantelli proved in their papers. If we measure the distance between the empirical and the truth by this maximum or sup distance, then they show this goes almost surely to 0, always, no exceptions. Wow. Almost no hypotheses except IIDF. Bingo. It looks like the truth. And so I claim that's the fundamental theorem of mathematical statistics in some sense, that the empirical, with data, we can recover the truth. Great. Here's a short proof. And this is not from their papers, and this is a modern proof. But it is now well known that if we give ourselves IID uniforms and let GN be the empirical of those, then the empirical from the data we started with has the same law, jointly in N and in X, as this uniform empirical composed on F. And that's a very simple fact. It's basically the inverse transformation. F inverse of uniform is distributed as X. And so that's easy to prove once you understand the uniform transformation. And so we get this supremum distance is equal in law to that one, but omitting the F, we get something bigger if F is continuous. And so this goes, F is continuous, we get equality here. But it's always bigger on this side. And so this guy can be shown to converge to 0 by just reducing to a finite grid using the monotonicity of both Gn and G, the truth. And so you get yourself down to a finite grid where you apply the strong law of large numbers, just the number of times you have grid points, or at most twice that. So it's a pretty easy proof, but in 33, well, that was the same year as Kolmogorov's Grundbegriffe, which established probability theory in mathematical terms. We were still struggling with basic things, and Glavinko proved this under the hypothesis that F is continuous. Cantelli noted that continuity of F did not matter. Cantelli proved that we could do without the continuity. So, good. In a sense, though, the first paper in this series was ahead, and Kolmogorov was already dealing with distributional issues. I'll come back to that in just a moment here. But let me show you, well, the statistics that Kremer investigated, first of all, and generalized by von Mises. Kremer proposed this L2 distance where we integrate along the whole line. And in general, for an F0, that need not be finite. we're integrating the whole line, and this is actually relying on some tail behavior of F0. So von Mises proposed putting a weight function, G, and Smirnov in the mid-30s modified further by changing G to psi of F0 and then integrating with respect to F0. And that makes things distribution free because we can say this is equal in law to something with Gn of F0, and then we can change variables. So all of a sudden we're down to distribution free by the mid to late 30s. And we've actually got what is known now today as the Kremer-von Mises statistic. And that's this last fellow right here. Okay. So here's the data that Kremer, one of the data sets that Kremer analyzed. It has to do with barometric pressure on a pretty good sized sample, 22,188. Of course, it was binned. It was discretized. And he has it presented in a table in his paper in a discretized form. And that's what it looks like when you plot it. And the magenta there, or the reddish, pinkish thing, is standard Gaussian. And what he's plotted are actually the standardized variables. These are the data minus x bar divided by sigma hat. So standardize the data. Is it close to Gaussian? And so that's what he's interested in. You eyeball that and you say, no, it's not quite, is it? Well, actually what he did, it's a fairly modern paper in some terms, because he was actually putting higher order approximations. He was fitting Graham-Charlier series, and he was actually doing adjustments for skewness and kurtosis and so forth. And he didn't stop with a picture like this. He actually went on to the pictures with skewness and with kurtosis. And you'll see the skewness measure here. That's the adjustment for skewness. And his paper actually does a statistical test in the sense of comparing the expected deviations. So he took expected value under the null of this statistic of his, which is an L2 distance. That you can compute to be just standard normal distribution, 1 minus standard normal distribution divided by n, plus a correction term due to skewness. And he actually computed numbers and got this thing to be something very concrete. And he did that for the data. Here's his Jn for the data. And he said, well, this isn't too much bigger than that, is it? Hard to tell. Hard to tell. And he brought that number down by doing higher order expansions. And so actually this was the worst data set in terms of getting normality, this barometric pressure data. And by the time he brought in the skewness and the kurtosis and correction factors, he got this number down to where it was much closer to that. And he says, well, it follows from this table at the average order of magnitude of the deviations. In no case exceeds. And that in no case actually goes across his other data sets. And his table actually had, this is just one data set. Pretty amazing paper. And Kremer himself was quite an amazing guy. He went on to become rector of the entire university system in Sweden and had a very, very long and illustrious career, academic in the sense of administering universities. This paper was just one of his early papers. He, of course, went on to write a famous book on mathematical statistics, which has first proofs of maximal likelihood converging to normal in the 40s. He was sort of ahead of the curve on that. And quite rigorous proofs for the time. Kolmogorov did propose this test statistic, square root of n times the maximal deviation. And if that true guy that we're hypothesizing here is continuous, then we're down to something that just depends upon maximal deviation of a uniform empirical from the truth. And he, in 33, in what to me seems to be way ahead of the time, actually showed that that has a limiting distribution, and here it is. And he did that more or less by reflection arguments, barehanded calculations, and his knowledge of Brownian motion. So he was already at the level of convergence and distribution. The papers that followed him in the Italian Actuarial Journal in 1933 were still back at the level of consistency. He had leapt ahead. He'd just jumped. Well, he was way ahead of his time. He was one of a group of mathematicians who had the knack of getting ahead, and we'll see other names in this category. This just repeats the page numbers again from the Italian Actuarial Journal. He knew the connection to a limit Gaussian process, and he just proved one instance, in some sense, of a general result. And many of you know, most of you probably know, what's coming next. But in the course of the late 30s and early 40s and into the 50s, this theory got formalized and developed further with the work of Doob in the late 40s, Donsker in 52, Prohorov, a general theory of weak convergence, at least for separable metric spaces, and Skorokhod in 56, starting to propose how we could get things close on one probability space and proposing wonderful metrics and on and on. I don't know if any of you have ever looked up Skorokhod on MathSciNet or on Wikipedia, but it's pretty amazing. He was a very productive guy. 400 papers, 40 books. I can't even begin to get close to Skorokhod. It's just phenomenal productivity and amazing insights into all kinds of things. So one of the real giants in this whole area. I couldn't find a picture of Monroe Donsker, but here are pictures of Doob, Prohorov, and Skorokhod. All of them are no longer with us. So let me just talk about this weak convergence theory just for a minute, because it sets the stage, the foundation for the modern theory. It sets up things in a way that we can understand today still. So this is a reminder. Gn is the empirical of uniforms. Un of t is the empirical process. That's what I call the empirical process. It has mean zero, has this covariance structure. And now I'm going to set up a corresponding Gaussian process with that same mean and covariance structure. And look at it for a minute. Well, if you think about the finite dimensional distributions, and here I just mean that process at a t1, dot, 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 up through a tk for any k and any t's between 0 and 1. Choose them however you want. The distributions of any such vector converge in distribution to the corresponding normal distributions for this vector u of t's, u of t1, u of tk. So that's just happening in k-dimensional Euclidean space. But the question was, really, do we have un converging in law or distribution to this process u, this Brownian bridge, as a function, as a sequence of random functions? And that's what this theory started with. And the question initially was in this metric space, D0, 1, with the uniform or supremum norm. And it turns out the answer to that is false. It doesn't happen. But it's purely a technical thing, in some sense. It's purely a measurability issue. So the answer to that question is formally stated mathematically, nope. Doesn't happen. But that's what Donsker proved in 52. So errors happen. People prove things that aren't true. And so the initial approach to this was a naive one in some sense. We thought we were going to be able to deal with the uniform metric. That turns out to be false. Let me just give you some pictures just to build intuition maybe. Here's the empirical distribution of a sample of size 5. These are just random numbers generated by me. I have complete control. I know exactly what they're coming from. There's nothing about real data here. But that's what the empirical distribution of a sample size 5 looks like. That's what UN looks like. Staircase guy for the empirical, and then it's a jig-jaggedy thing for the UN, with these slopes being minus n to the plus 1/2. So these slopes are all negative on the pieces that are continuous. The jumps are all of size n to the minus 1/2. So the jump sizes are coming down. Slopes are getting bigger. And so you go up in sample size and you start getting pictures like this when n is 100. There's the GN, there's the UN. And when you go up to 2,000 or so, we're graphically illustrating that the Glevenko-Cantelli theorem is true. The GN gets close to the line. And here's UN. And if you start looking at the fluctuations here, you start seeing, oh, well, Kolmogorov's theorem is true, and that the magnitude of those fluctuations is not changing with n. It's stable in n. It's roughly the same, no matter whether I'm looking at 5 or 100 or 2,000. Kolmogorov's theorem is true as well. Good. So Doob suggested in 49, continuous real-valued functions G, mapping D01 into R. This is discontinuous functions that are continuous from the left. No, limits from the left, continuous from the right. CADLAG. Suppose we've got Y's in there. Well, we should expect that G, any old continuous guy in some sense, we have convergence in law. So real valued functions should converge. And so here are several examples of functionals. We should have convergence. There's the maximum. Whoops. What did I do? Panic. Here we go. There we go. Okay. Well, there's maximum. There's Cramér-von Mises type functional. There's time the process is positive between 0 and 1. Well, all these cases, Doob was saying we should have this being true. And his argument was with modified notation to match what I'm doing in my notation. We shall assume until a contradiction frustrates our devotion to heuristic reasoning, if it locks. Well, anyway, his heuristics led to Donsker's proving this in 1952, and that's true up to measurability issues, which got straightened out gradually over a long period of time between the 50s and the late 60s. And Billingsley's 1968 book gave a very nice explanation, and this is originally due to Chibisov in Russia, pointed out the difficulty. Turns out the empirical is just not measurable with respect to this supremum metric. This space is D01 with the supremum metric is an inseparable Banach space. And inseparability gives rise to all kinds of complications, including this lack of measurability. So people tried to find all kinds of solutions over time, and gradually umpteen different solutions were proposed, and gradually people came to understand why it was working the way it does. And it led to a completely new theory about 20 years later, quite a long time later. It took a lot of work. In between, there was a lot of work on exponential bounds for these random functions. And one of the big names in the terms of exponential bounds was this inequality due to Dvoretsky, Kiefer, and Wolfowitz in 1956. And they proved that the chance that the positive deviations of the empirical being bigger than lambda are bounded above by some absolute constant times exponential of e to the minus, 2 lambda squared. They did not specify c. De Vroy and Wise proved in '79 that c being 306 is okay. It had been conjectured already in Birnbaum and McCarthy in '58 that 1 would work based on numerical experiments. Galen and I contributed to the confusion by proving c is 29. Works. Student of Dave Siegmund's at Stanford proved in '85 that 2 square roots of 2 works. And finally, Pascal Massart in 1990 proved that c equals 1 works. And that's very beautiful. That's very wonderful and sharp. Nothing can be better, because that is the limit distribution. Bang, right on. Took a long time to get there. And in some sense, this encapsulates what's going on in empirical process theory. One aspect of empirical process theory these days is we have lots of results that are analogous in the modern theory to the original statement of Kiefer and Wolfowitz. And we're only beginning to make corresponding adjustments or improvements. And we have problem after problem where we have bounds up to some constant and we don't know sharp constants. And increasingly in the research that's going on today, we need to know the constants better. For lots of things in high-dimensional statistics in particular, we need very much more precise control of constants. So this is a poster child for other developments that are still going on in other parts of empirical process theory. Here are pictures of Dvoretsky and Kiefer and Jacob Wolfowitz, Jack. I had the pleasure of meeting Jack Kiefer briefly at Cornell while I was at Rochester in the late '70s. And here he is doing his hobby. What's his hobby? He was a mycologist. He was an expert in mushrooms. And he became very renowned as well for his statistical work as for his work on mushrooms and their terminology. So this is a growth of mushrooms on a tree. I'm not sure where, but Jack was quite a mycologist and expert in that area. There's Pascal Massart. Pascal is still producing lots of nice research. Well, there were a lot of further developments in this one-dimensional theory, and I've just listed a few of them here. There were proofs of stronger modes of convergence, laws of the iterated logarithm, strong approximations, starting with Skorokod and Brillinger. Those proved to be very useful in various things in statistics. So it got developed still further by the Hungarian school, Komlosmeyer and Tushnadi, in the mid-'70s. Proved very sharp and refined theorems about how close we could put empirical and Gaussian on the same probability space. And that series of papers went on through the '80s and into the late '80s. And I think of the Mason and Van Sweat and Bretignolles and Massart papers as being sort of the culmination of that work for the uniform empirical. We developed limit theorems for the standardized or normalized empirical process after we divide by root t times 1 minus t. Those are theorems that were proved in Germany by Jaschke and Eicher. And we developed theorems for the oscillation moduli of this thing. How much does it wiggle? And got very precise control of these quantities. All of those developments, well, they went on over a long period of time. Most of them are summarized in this wonderful book that Brett held up earlier. If you really want to get all this At least most of it is in that book still. Some of the modern developments as of Mason and Van Zwatt or Bratignolles and Massard are not there. But for example, these theorems have proved to be very useful in dealing with modern methods for combining p-values. The higher criticism statistics that have been studied by Dave Donahoe and his student Jashan Jin, those higher criticism statistics and ways of combining p-values and doing multiple testing, the limit theory for them is dependent upon limit theory for that soup right there. And without understanding of this, it's hard to understand what those combination of tests are doing. But I want to leave the one-dimensional story. So I'm now making a transition. I'm leaving the one-dimensional picture. I'm way behind schedule, so I'm going to have to speed up. It's going to start compressing. The transition period, as I say, started in about 53. People started thinking about, oh, what if we had vectors of data? What if the x's are not just real value, but we have vectors? Well, then a clear analog of the empirical is to form things coordinate-wise and think about xi's being less than or equal to little x as vectors coordinate by coordinate. So that's a clear analog. And it leads to thinking about x's being in lower left orthants. That's Pn, or the empirical measure, of an orthant. That should be a little x over there rather than a cap x, perhaps. This is R. Looks almost like a cap x, but that should be that's a little x. And it's just coordinate-wise ordinary. And this now is the empirical measure, not the empirical distribution. And so it becomes very quickly apparent that what we really want to know is, well, what if I consider other classes of sets, not just rectangles, but I think about some class of subsets of the space on which I'm defining things, this sigma field. What if I take the maximum of the empirical measure and the true measure over some class of sets? When do we have that holding? And that's the modern framework for Glubenko-Cantelli theorems for sets. And if this holds, we're going to say C is a Glubenko-Cantelli class for P, and you write that. Okay, well, other classes. How about rectangles or boxes, half spaces, balls or ellipses, convex sets or lower layers? And once you're done with all the sets that you want to think about, how about functions? Why restrict the functions that are bounded by 0 and 1, or just taking two values? Why not think about functions that map the sample space into R? And so here's the notation for the rest of the talk. P of f is going to be the integral of f dp over the sample space. Pn of f is the integral of f dpn over the sample space, and that's just the averages of the f's at the data points. And that's just notation. But it makes it clear that Pn, considered indexed by functions, is just keeping track of a whole bunch of averages. We really are just talking about a whole bunch of averages, and we let f vary over some class. Okay, well, that's great. Here's the early history of this as I know it. Forte and Morier in 53 proved that C, the class of half spaces in RD, if P is absolutely continuous with respect to Lebesgue measure, has a density, then that's Glubenko-Cantelli. That's what Forte and Morier proved. Jacob Wolfowitz in 54 proved that that still works if P is arbitrary without the restriction. Julius Blum in 55 looked at lower layers. Lower layers are a class of sets that have to do with slicing through and looking at level sets of functions that are monotone along coordinate axes in all dimensions. So you take a function that's monotone along all coordinate axes, slice through it, you get lower layer sets. That's of interest in shape-restricted inference for monotone decreasing functions, which is part of the theme of my talk tomorrow, shape restrictions. And so that will, well, come back vaguely, but not strongly tomorrow. This last chap, John de Hart, I always thought, until I prepared for this talk, that he was German. And he's not. He was a very American guy. Did his PhD in Missouri. Was talking to Dan Brunk. Brunk was motivated by shape restrictions, wanted to know about lower layers. And so de Hart answered questions that Blum raised, and he gave the first general bracketing Goulenko-Cantelli theorem. And he gave necessary sufficient conditions on P for lower layers to be Goulenko-Cantelli, but there are some restrictions needed. So we're almost at the end of this intermediate period. Here's Edith Mourier. I couldn't find pictures of Forte. Haven't found pictures. You've seen a picture of Jack Wolfowitz. I didn't find a picture of Julius Blum. This is Edith Mourier in 1971 in a meeting in Prague. You'll see down in the corner of these pictures, I must thank the Ober-Wolfach photo collection. This is from the Ober-Wolfach photo archive. And a lot of these photos are from that source. So for half spaces, what does it look like? Well, here in R2, if this magenta thing is the unit circle, unit sphere in R2, and that point represents the unit vector in that direction, going off this way. So this is the one-dimensional space spanned by that vector. Then half spaces can be described by just projecting vectors in the plane onto this line and seeing whether they're to the left or right of a given point. So the half space here is just everything down there that's shaded, and it goes off to infinity. And that's the set that's described by that direction and this distance from the origin. So what we do, if we've got data, that's a number of points from one of our favorite distributions on R2. That's just standard Gaussian, independent Gaussians both ways. We project those guys onto this line and do the empirical along that line. And this is the way Jack Wolfowitz proceeded. He didn't quite do it this way, but close. He says, once we're on that line, we know Goulenko-Cantelli theorem holds for that first direction, that fixed direction. Got a fixed direction, now I'm on a line. I just have Goulenko-Cantelli for each fixed direction. And now if I can get that uniform in directions, I'm in. And that's what Jack argued in his proof. He showed that you could make it uniform in whichever line you took. So you take another line, and you'll get the same property holding. And it didn't depend upon which direction you were looking. And so that was Wolfowitz's proof. Well, here we capture in one dimension the standard normal Gaussian. That's the empirical of what I saw along that line. Of course, this is a basic thing in modern statistics. We project onto lower dimensional spaces and look at empiricals on lower dimensional spaces. And this process of doing projections onto lower dimensions is fundamental to what we do all the time. It's just very basic. Well, what we realized at about this time, or other people, smarter people than me, realized was that half spaces are very different from things like lower layers or convex sets. And half spaces are basically parameterized by something that's d-dimensional or d-1 dimensional and a one-dimensional thing. So it's roughly a d plus one dimensional thing. And these sets have some very strong combinatorial properties, which I'll talk about in just a minute. But here's the final version of the Goulenko-Cantelli theorem via bracketing. So now we have X's IIDP on a general sample space. This is de Hart, 1971. And here's the freedom. We've got up to a general sample space, not just the real line, not just RD. General. Let this be a collection of measurable functions. with finite means for real valued functions L and U on that sample space. Let LU be the set of f's that are between the lower function and the upper function for all x. So that's uniform in x, between. This is a bracket. It's an epsilon bracket if some norm of it is less than epsilon for functions f. Okay, the bracketing number is going to be just the count of this, the minimal number of epsilon brackets needed to cover. Oh, I've got to count something. I've got work to do, mathematical work. Can I make this come under control? If I can, then I've got to go to the Cantelli theorem. That's what DeHart proved. If this number is finite, here I should have finite for every epsilon. I've missed a symbol. If that bracketing number is finite for every epsilon positive, then this difference, Pn, looks like P uniformly over that class. Wolfowitz's proof of his theorem for half spaces was basically of this flavor, bracketing. And it works here. For this small class, the bracketing argument works. And this works for bigger classes if you can do the count. But there were three statisticians who were really ahead of their time. I want to mention them briefly. Abraham Wald was essentially doing bracketing in his proof of consistency of the maximum likelihood estimate in 1949. If you break down his argument, it is a bracketing argument. It was just bracketing. Lucien Lacombe noticed that or recognized it. I don't know exactly in which paper of Lucien's this appeared or if it ever did appear, but Tom Ferguson credits Lucien with this version of the theorem. And Peter Huber, in the late 60s, was way ahead of his time in formulating things in empirical process terms, in terms of counts and of oscillation phenomena that are related to empiricals. So these are three guys in statistics who were sort of keyed into empirical process type arguments way ahead of the rest of the field, and were really ahead. Wald's theorem, as formulated by Lacombe, says, well, suppose I've got functions f that are indexed by a parameter theta, and these functions are continuous in theta for p almost all x. Suppose that theta is compact and that this has an integrability. So I take the sup over the thetas of the f of x's. I get an envelope function. This is not a distribution function. It's an envelope function that satisfies, well, it's integrable. Then I do have finite bracketing numbers. The compactness plus the continuity of the maps yield bracketing. And that's what Lucien recognized somewhere. And it might have been in lectures at Berkeley. And Tom Ferguson took courses from Lucien at Berkeley and knew about it from there. But they were fundamentally doing bracketing way ahead of time. Abraham Wald, Lucien Lacombe, Peter Huber. Peter is still with us. Abraham died young, as many of you know, in a plane crash in India, not long after his paper in '49. Lucien had a very long and productive career and was one of the giants of our field in theory. So, what happened to get the theory generalized even further? Well, it was the Russians. And I've given a brief indication of where I'm going in this last few minutes. And I'm going to have to stop before I finish. But Vapnik and Chervenikis in 1968 published a paper in Russian in the Theory of Probability and Applications, which had to do with the uniform convergence of frequencies of events to their probabilities. It was reviewed by Dick Dudley. This is an object lesson. Dick Dudley reviewed papers from Math Sci, the Math Reviews, starting not long after his PhD in 1966 and going up until late in his career. Between 1966 and 1975, Dick Dudley wrote 142 reviews for Math Reviews. 142. Think about it. That's one a month. More than one a month. A tremendous number of reviews. Moreover, he had a leg up on all of us. Dick knew a bit of Russian, and he could read and understand the Russian. And so he understood what was going on. The following very interesting results are announced. Example, C equals RD, C equals all half spaces. The VC theory is underway. Half spaces have connections to this VC theory that says if you consider how many points from a list of points that you can pick out by half spaces, by intersecting this list of finite points in the space with all the half spaces, if the number of points you pick out at a certain stage becomes less than all subsets, and in this case for half spaces, it turns out less than all subsets is, well, this list has to be D plus 1 or 2 long. You get something that's very remarkable. You don't get something growing as 2 to the n, the number of all subsets. You get something growing as n to a power, n to a dimension, much, much smaller. And the VC theory really gives amazing control just from this combinatorial property, how many things you can pick out from a finite list. So half spaces fall in that category, and Dick knew it from reading their paper and reviewing it. This appeared in English translation in 1971. Dick says, this is an if and only if theorem. The reviewer finds these results striking and unexpected. Striking. Amazing. Well, there's Vapnik, there's Cherveninkus, there's a very young Dick Dudley. 2 of them are still with us. Cherveninkus is not. Well, their theorem says, and this is as formulated after some work, another 10 to 15 years. Their initial paper, reformulated for functions, says if I have an empirical count of how many balls it takes in L1 to cover a truncated function class, if this divided by n goes in probability of 0 for every epsilon and m, this is if and only if this converges. It's not just one direction, it's if and only if. It's a very, very fine, sharp theorem. And this is as a result of the evolution of this type of theorem, starting with Vapnik and Cherveninkus and going through the paper of Genet and Zinn in the early 80s, 84. Well, counting, how many balls cover? So to do this modern theory, you have to have control of these counts, and you have to get good at counting and controlling how many balls of size epsilon does it take to cover, and that's the basis of the whole thing. So it's really very simple. You break things down into what the process is doing at these finite points, the center of the balls. You control how much it fluctuates away from those points. So it's bookkeeping once you've got the idea in mind. And so half of this yellow book is the bookkeeping, just that basic idea. Control at finitely many points, control the fluctuations away. And those fluctuations involve these counts, how many balls. Well, symmetrization by Rademachers is a key thing in this proof. This is one example of what happened in the 80s and 90s with insertion of some other variables here in the empirical process. These epsilon i's being plus or minus 1s with probability of half each give us a bound, and that's a symmetrization bound. Then the key thing is to condition on the xi's and use that sums of Rademachers are sub-Gaussian. Well, that's the outline of the proof. It's a very simple proof in some ways, but putting all these things together is what the theory is about. This idea, though, of inserting random variables here was the other key thing that developed over the next few years, and this is fundamental. So by the late 70s, we had a good Donsker theorem. Here's the general framework of limit theorems. Here's a p-Brownian bridge, symmetric on that space, given by variance, pseudometric. And as indexed by functions, this is the empirical process. And Dick was the very first one to prove that we have convergence in that framework. But I must say he had a leg up on us in several ways. Not just Vapnik and Chervonenkis, but he'd also written a key paper in 1967 which described the continuity properties of Gaussian processes very generally. And Dudley's entropy integral is this thing right here. That's a sufficient condition for continuity of Gaussian processes. That's very widely known now as Dudley's entropy integral. Dick is a very generous and kind fellow, and he's written a paper recently which says, this is not my entropy integral. This is due to Sudakov. Give credit to Sudakov. He's very honest, and he gives the whole history of Sudakov's involvement with it. And I think he's too late. We've got an example here of Stiegler's law that things get named after other people. Well, by the end, mid-'80s, we had good central limit theorems for functions indexing. There's a sufficient condition due to Pollard and Kolchinsky. This is kind of a uniform entropy. We take the log of the count, L2 balls, and then we have to soup over Q's that are finitely discrete. Well, if that condition holds, then we have weak convergence over this whole class. That holds if we just have a growth of these counts that's of this form less than 1 over, well, epsilon to the minus r with r less than 2. Dick Dudley, David Pollard, Vladimir Kolchinsky. I'm getting to the point where I have less detail about the individuals. I don't even know when Vladimir was born. It's about 1950. Minna Osiander in our Department of Statistics at the University of Washington proved a bracketing central limit theorem in about 1984. This was in her thesis. This was one of the first PhD theses in the Department of Statistics at the University of Washington. It was done jointly with Ron Pike and Rich Bass. But she proved that under this bracketing condition, again, an integral condition on bracketing, the growth of bracketing entropies, we get this weak convergence. Minna, still at Oregon State, Rich Bass, and Ron Pike. Multiplier central limit theorems. I'll go through this very quickly, and then I'll close. So here's Z's that are IID with values in a Banach space, a big space of vectors or functions. You want to think about these as the Z's are random functions, say in C01, continuous functions on the unit interval, or maybe they're just long vectors in RD. Let Y's be IID real valued, expected value 0, finite variance independent of those guys. This is the partial sum or the mean normalized in the Banach space. This is the multiplier quantity that's corresponding with these yi's inserted. Well, in the 80s and 90s, mid-80s and 70s and 80s, people in probability and Banach spaces were interested in when does that weak convergence occur? When does this sum converge in law? Well, then when does this converge? And then when does this converge conditionally upon the Z's? In probability or almost surely. And most of this investigation was entirely separate from any statistical motivation. Sorry. They were just having fun, doing probability. They were just playing games of probability, trying to understand what happened. And amazingly enough, the answer is, well, yes, if this is tight, if you let CLTZ be this soup of how big the norms get in the Banach space expected, souped over n, well, the answer to question 2 was in the multiplier thing. If these y's are L21, then you get inequality that goes like this. And that's very nice because this quantity is bounded both above this quantity, the multiplier thing, is bounded above and below by something involving constants times CLT for Z. That's a multiplier inequalities. That was used by Genet and Zinn in '84 with Y being normals, and they used this to Gaussianize empiricals and get Gaussian processes and study things in terms of Gaussian processes. Ledoux and Talleyrand in two papers in '86 and '88 said, yes, the answer is positive for question 3. If we've got that much integrability of the multipliers, we're in business, and we have weak convergence to constant times thing we had originally. Wow. That's essentially what we do in the bootstrap. And Genet and Zinn understood this. And their paper in 1990 said Efron's probability bootstrap, Efron's bootstrap works for empirical measures. Here's Pn hat. These are multinomial weights. Those are not independent, but they're multinomial, marginally binomial, coordinate-wise. Bootstrap empirical process is defined this way. It just involves these multinomial weights times things coming from the data. Well, we all know that these multinomial guys, because we're dealing with 1 over n probabilities, sample size n, those converge in law marginally to Poisson. And on the other hand, if we took a Poisson sample size, then those things, as a vector, is IID. So if you Poissonize, you make things independent. It puts you in the situation of the multiplier central limit theory. And lo and behold, Genet and Zinn proved in 1990 the following are equivalent. F is P Donsker. F is bootstrap P Donsker in probability. And the amazing thing about that is it's if and only if it's tight. There's no wiggle room. We've got exact control. We know exactly what's going on. And the proof is basically the multiplier central limit theorem with IID-centered Poisson ones, and then coupling up, de-Poissonizing, essentially, getting rid of the Poisson. Michel Ledoux and Michel Talleyrand are two of the big names in probability and big spaces. They're the ones who did these multiplier central limit theorems in the 80s without any real thought of statistics. Both of them have contributed enormously to concentration of measure inequalities, which are driving a lot of inequalities in modern statistical theory. The concentration of measure results derive from these two guys, and very clever work by both of them. And a whole bunch of further developments since. Evry Genet and Joel Zinn. Evry's just passed away earlier this year. Joel is still with us. Well, the future. I can't say much the last 20 years. I've left out that the last 20 years there's a whole lot going on with dependence. There's more copying with concentration of measure. There's a lot of things going on with high-dimensional data, trying to control constants and inequalities so we can let dimension go up in the parameter spaces. Two of my favorite areas are the one my colleague in the Netherlands has been pushing, non-parametric Bayes methods. He is using empirical process methods essentially every day to prove things about non-parametric Bayes. I'm interested in shape-constrained estimation. I've been playing games with shape constraints, and that's what I'll talk about tomorrow. And with that brief introduction to the future, which I really can't predict at all, I'll close. Thank you very much. I apologize for going too long.
I have a question. In the book by Circling, Approximation Theorems of Mathematical Statistics, he gives a very, really very quick proof of the Goulenko-Cantelli theorem using the Deveretzky-Kiefer-Wolfowitz inequality.
Yep.
And actually it results in a stronger theorem,
Yes.
version of
Sure.
Goulenko-Cantelli, because you get complete convergence in the sense of skew and Robbins. And my question is, are there, for the more general sample spaces, are there analogs of
Yes, there are. And again, that has to do with my explanation about constants and so forth. Michel Talleyrand in 1994, in a major paper in the Annals of Probability, proved very nice analogs of Dvoretsky-Kiefer-Wolfowitz type inequalities under entropy-type conditions. And so if we have entropies or covering number growth that is polynomial, you typically get a power of t out in front, and there's an e to the minus 2t squared, or lambda squared.
So you can get complete convergence.
You could get complete convergence. The difficulty in using these things in high-dimensional statistics and modern theory is that we still don't have adequate control of those constants out in front. And so we don't yet have enough knowledge of how those inequalities work in a variety of scenarios. They are very nice inequalities, and that was one of the first major applications for statistics of some of Michel Talleyrand's concentration of measure ideas. There's one way in the back. Oh yes, well, the finite dimensional laws of even the uniform empirical process converge to finite dimensional laws of the Brownian bridge simply by the multivariate central limit theorem. So that finite dimensional convergence, even for general processes, even in these abstract settings, that's all driven, the finite dimensional convergence is driven simply by the multivariate central limit theorem. The processes are very nicely linear. You can use Cramer-Wold device to get from k dimensions to 1 dimension. You crank through the apparatus of Cramer-Wold, and the finite dimensionals just converge very nicely. The whole difference comes in proving the tightness, proving that you don't deviate too much in small balls around these points. And so that's where the real differences come in, and that's where the work begins. And that's where empirical process theory, the modern theory, gives us a whole set of tools to handle maxima. And that's really the current state of affairs, is that empirical process theory, this theory we've developed for proving these convergences, gives us a whole variety of tools and techniques for controlling maxima and how big are things.